Welcome to our deep dive into the formation of galaxies, a process that spans billions of years and involves a complex interplay of gravitational, physical, and chemical processes. From the unimaginably dense and hot conditions of the Big Bang to the majestic spiral and elliptical galaxies we observe today, this epic journey takes us through the very evolution of the universe itself. Imagine a universe without galaxies. A universe filled with a formless sea of particles. It's hard to fathom, isn't it? Yet that was the reality of our universe for a period. Over eons, gravity sculpted these particles into the grand structures we see today. Each galaxy a cosmic ecosystem teeming with stars, planets, and the potential for life itself. In the beginning, there was the Big Bang, an event not of destruction but of creation. Imagine, if you will, all of space and time condensed to a point smaller than an atom. Then an expansion, not an explosion as we traditionally think of it, but an expansion of space itself. The universe, in its first fleeting fractions of a second, inflated faster than the speed of light, a period we call cosmic inflation. This rapid expansion wasn't chaos, but a process governed by laws of physics, laws that continue to shape the universe today. As the universe expanded, it cooled, and energy began to condense into matter, the first elementary particles flickering into existence. Imagine a sea of quarks, leptons and bosons, a chaotic soup of primordial ingredients. It's within this energetic cauldron that the seeds of our universe, and ultimately of ourselves, were sown. The early universe was a hot, dense fog of protons and electrons, a plasma opaque to light. Photons, the particles of light, constantly bounced off free electrons, unable to travel freely. As the universe cooled, recombination occurred. Protons and electrons combined, forming the first neutral hydrogen atoms. Photons were finally free to stream through the universe. This first light is still detectable today as the cosmic microwave background radiation. With the formation of neutral hydrogen, the universe plunged into darkness, a period we call the Cosmic Dark Ages. Imagine a universe devoid of stars, a vast expanse of mostly hydrogen and helium gas. But within this darkness, gravity was at work, slowly pulling matter together. Minute density fluctuations, tiny ripples in the fabric of space-time left over from the Big Bang, acted as seeds for the growth of structure. These overdense regions, though infinitesimally small compared to the vastness of space, had slightly stronger gravity than their surroundings. This subtle difference was enough to draw in more and more matter, slowly but surely building the foundations for the first stars and galaxies. The Cosmic Dark Ages weren't a time of inactivity, but rather a period of gestation, a time when the universe was quietly assembling the ingredients for its next grand spectacle. Driven by gravity, clouds of hydrogen and helium gas continued to collapse, their cores becoming denser and hotter. Imagine the immense pressure and heat building up within these collapsing gas clouds, a cosmic pressure cooker on a grand scale. Finally, the critical threshold was reached. The cores of these clouds became hot and dense enough to ignite nuclear fusion, the process that powers stars. The first stars, massive and short-lived, blazed into existence, ending the Cosmic Dark Ages. These first stars, known as Population 3 stars, were unlike any stars we see today. Composed almost entirely of hydrogen and helium, they were colossal, hundreds of times more massive than our Sun. These stellar pioneers lived fast and died young, their intense radiation ionizing the surrounding gas, a process that shaped the evolution of the early universe. Their explosive death seeded the cosmos with the first heavy elements, the building blocks for future generations of stars and galaxies. As more and more stars formed, gravity continued to draw them together into larger and larger structures. Imagine these early star clusters, drawn together by their mutual gravitational attraction, slowly coalescing into larger systems. These proto-galaxies, the precursors to the majestic galaxies we see today, were irregular and clumpy, constantly interacting and merging with their neighbors. Imagine a cosmic dance of proto-galaxies, drawn together by gravity, swirling and merging in a chaotic ballet. These mergers were violent events, triggering intense bursts of star formation as gas clouds collided and compressed. Over time, these mergers smoothed out the irregular shapes of proto-galaxies, shaping them into the spiral and elliptical galaxies we observe today. This process of galactic assembly wasn't a one-time event, but an ongoing process that continues to this day. Our own Milky Way galaxy, for example, is thought to have formed from the merger of numerous smaller galaxies over billions of years. While we can observe the luminous matter in galaxies, stars, and gas, there's an invisible component crucial to galaxy formation: dark matter. Imagine a scaffolding, invisible to our eyes, providing the gravitational framework for galaxies to form. Dark matter, which doesn't interact with light, makes up most of the matter in the universe. Its gravity shaped the large-scale structure of the universe, creating the cosmic web of filaments and voids we observe today. Galaxies come in a variety of shapes and sizes, each a testament to the complex interplay of gravity, gas dynamics, and star formation. Imagine the diversity of galactic architecture, from majestic spiral galaxies to massive elliptical galaxies. Spiral galaxies, like our own Milky Way, have flat disks, central bulges, and spiral arms. Elliptical galaxies are generally smooth and featureless, with little ongoing star formation. Beyond these, there are irregular galaxies with no defined shape. Each type of galaxy tells a unique story about its formation and evolution. Within galaxies, stars are constantly being born, living out their lives and dying, enriching the interstellar medium with heavy elements. Imagine the cycle of stellar birth, life and death, a cosmic dance that plays out over billions of years. Star formation begins in cold, dense clouds of gas and dust, known as molecular clouds. These clouds, often found in the spiral arms of galaxies, provide the raw materials for new stars. As gravity pulls these clouds together, they fragment into smaller clumps, each of which can collapse to form a star or a system of stars. Imagine these stellar nurseries where new stars are constantly being born, illuminating the surrounding gas and dust. The process of star formation is a delicate balance between gravity, which pulls material inward, and radiation pressure from newborn stars, which pushes material outward. Galaxies are not randomly scattered throughout the universe, but are organized into vast structures, from small groups to massive clusters. Imagine a cosmic web of galaxies, interconnected by gravity, forming a vast network across the universe. Galactic clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. These clusters are filled with hot X-ray emitting gas and are thought to be still growing, attracting new galaxies over time. Our own Milky Way galaxy is part of a small group of galaxies known as the Local Group, which is itself part of a larger supercluster called Laniakea. Imagine our place in this cosmic hierarchy, from our local neighborhood of galaxies to the vast superclusters that span billions of light years. The study of large-scale structure helps us understand the distribution of matter in the universe and provides insights into the nature of dark matter and the evolution of the cosmos as a whole. Our understanding of galaxy formation is constantly evolving as new telescopes and simulations provide us with ever more detailed views of the universe. Imagine the frontiers of astrophysics, where scientists are pushing the boundaries of knowledge, seeking to unravel the mysteries of the cosmos. Advanced telescopes, both on the ground and in space, allow us to peer deeper into the universe than ever before, observing galaxies in their earliest stages of formation. These observations provide crucial data for testing and refining our models of galaxy formation. Computer simulations, which can model the complex interplay of gravity, gas dynamics, and star formation, allow us to recreate the evolution of galaxies over billions of years. These simulations help us understand how different physical processes contribute to the diversity of galaxies we observe. The study of galaxy formation is a vibrant and active field of research, with new discoveries and insights emerging all the time. Thank you for joining us on this journey through the cosmos. From the Big Bang to the majestic galaxies we observe today, we've explored the epic story of galaxy formation, a story that spans billions of years and involves a complex interplay of physics, chemistry, and the fundamental forces of nature. As we've seen, our understanding of galaxy formation is constantly evolving as new observations and simulations provide us with ever more detailed views of the universe. The quest to understand these celestial wonders continues, driven by our innate curiosity and our desire to unravel the mysteries of the cosmos. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating insights into the universe. Until next time, keep looking up and never stop exploring the wonders of the cosmos.